Good morning, dear student. In previous lecture, we already discussed the PCS theory of superconductivity. So, in this lecture, we are very much interested the important phenomenon that is Mesner effect. So, what is this Mesner effect, and how the superconducting material shows Mesner effect? So, we will discuss this Mesner effect in this lecture. So, before discussing the Mesner effect, let us discuss the definition of this Mesner effect. So, first, definition. So, what is this Mesner effect? When a superconducting material, when a superconducting material, when superconducting material is placed in a magnetic field, in a magnetic field and cool, in a magnetic field and cool below the critical temperature, and cool below the critical temperature, cool below the critical temperature, it behave as it behave as diamagnetic material, it behave as diamagnetic material, it behave as diamagnetic material and repel and repel and repel and repel magnetic lines of force, and repel magnetic lines of force. This effect is known as Mesner effect. This effect is known as Mesner effect. If you consider once again the definition of this Mesner effect, what is this Mesner effect? When a superconducting material, so we already discuss the difference between normal conductor and superconductor. Superconductor is a material, so when it is cool below its critical temperature, it will show superconductivity. So above critical temperature it becomes normal conductor, and below supercritical temperature it is superconducting state. So when a superconducting material is placed in magnetic lines of force or in place of magnetic field, and it is cool below its critical temperature, it behave as a diamagnetic material. So we already know what is meant by the diamagnetic material. So it will shows the behavior such as it will shows the behavior like diamagnetic material which shows in magnetic field and repel the magnetic lines of force, and this effect is called as Mesner effect. Again, one more definition is there. When a magnetic field is applied to a superconductor species at a temperature below its transition temperature, the magnetic lines of force are expelled, and this material act as a diamagnetic material, and this effect is called as Mesner effect. Only the slight modification is there, but you should remember what is when a superconducting material it is placed in magnetic field, and if it is cool below its critical temperature, then it will shows superconductivity, it will behave as a diamagnetic material and repel the magnetic lines of force, and this effect is called as Mesner effect. So the question is asked in examination, that what do you mean by Mesner effect, and prove superconductors are perfectly diamagnetic material. So how will you prove the superconductor is diamagnetic material? So this is the definition of Mesner effect. Let us discuss some graphical representation to understand the Mesner effect. So if you consider, this is the material, this is a material, okay, and we applied the magnetic field, so magnetic lines of force. So if we see this case, that is a material from which these magnetic lines of force are passes, or it carries the magnetic field, okay, it will shows the magnetic lines of force are passes and the resistivity is not equal to 0 in this case. So this is the case where the temperature, it is greater than Tc, critical temperature or transition temperature. And if you see, this is a normal state. Normal state, magnetic field is passed from this material when temperature it is greater than critical temperature. So when temperature it is higher than critical temperature, then the magnetic lines of force are passes through the material. When this material get cool, this material get cool, so the temperature is decreases, means the condition is Tc, critical temperature, it is greater than the temperature, that is higher temperature. So Tc means what? The critical temperature below which the material act as a material becomes a superconductor. So we already discussed the definition when this superconducting material. So this condition indicate that the material is superconductor. This condition indicate that the material is superconductor, and if you consider uh, this state, it is a superconducting state, and this material, if you consider this, this is the material, and it will expel out the magnetic lines of force. So there is a no effect of this magnetic lines of force. So if you see this, so this is the effect. So we get such a kind of diagram for the superconducting material, that is the magnetic lines of force are expelled out. Magnetic lines of force are expelled out. Magnetic lines of force are expelled out. Magnetic lines of force are expelled out, and this is known as a Mesner effect. When if you consider, this is also a superconductor material, but the condition is what? It is the condition, that is when temperature it is greater than the critical temperature. So above Tc, the material act as a normal conductor, so it does not show the resistivity is 0. But when it is cool and we apply magnetic field, then the material is perfectly in superconducting state, and it will show the phenomenon such as diamagnetism, because it expel out the magnetic lines of force. So there is a no magnetic line, so there is no effect of magnetic lines of force on this superconductivity, and the material is perfectly diamagnetic. So as the diamagnetic materials are expel out these magnetic lines of force, same in this superconducting material also expel out the magnetic lines of force, and it becomes perfectly diamagnetic. Again, if you see, the condition is the critical temperature, it is greater than the higher temperature, so the material is in superconducting state. In this case, if you consider the value of this magnetic field, the magnetic field is 0. The magnetic field is 0. So there is no effect of the magnetic field because the magnetic lines of force are expelled out by this superconducting material. So this is known as a Mesner effect. So whenever a superconducting material it is placed in a magnetic field and cool below its critical temperature, it behave as a diamagnetic material and repel the magnetic lines of force, and this effect is known as Mesner effect. uh, so how will you prove that this superconducting material it is perfectly diamagnetic? So we will use some terms and a mathematical equation to show that the superconducting material below its critical temperatures are perfectly diamagnetic. Let's consider one by one. That is, if you consider the flux density in magnetic material, so flux density it is denoted by symbol B. uh, if you consider the magnetic flux density B vector, let us consider it is a vector. Flux density that is denoted by B vector in a magnetic material, the magnetic flux density that is B vector in a magnetic material, is related to the strength of to the strength of to the strength of applied magnetic field, to the strength of applied magnetic field applied magnetic field to the strength of applied magnetic field by equation B vector, which is equal to mu 0, that is your constant, in bracket H vector plus M vector. So if you consider the first one, that is so in this equation B vector it is your flux density and it is related to the strength of applied magnetic field. So H vector, so in this case H vector it is your applied field strength, strength of magnetic field, applied field strength, and the M vector it is your the intensity of magnetization, intensity of magnetization intensity of magnetization. What is this M vector? It is intensity of magnetization, and it is the property of material, which plays in a magnetic field, and how much magnetic field it gain, that is nothing but the intensity of magnetization. And H vector is the applied field strength and B vector is a flux density. So according to the Mesner effect, so what Mesner effect indicate? according to the Mesner effect, when temperature it is, that is critical temperature it is greater than higher temperature, then the B vector, that is magnetic flux density, is equal to 0. Magnetic flux density is equal to 0. So what you get? 0, which is equal to, let us consider this is equation 1. So equation 1 becomes 0, which is equal to mu 0 H vector plus M vector. So we get this is equation second. So the first equation, the relationship between magnetic flux density, applied field strength, and the intensity of magnetization. But according to the Mesner effect, when critical temperature it is higher, when critical temperature it is greater than the normal temperature, then the B magnetic flux density, so there is no magnetic field effect, so B vector is equal to 0, and we get equation second. So from this equation second we can write, H vector plus M vector which is equal to 0, or we can write from this equation H vector which is equal to minus M vector. So we get equation 3. And we know that the magnetic susceptibility, if you consider the magnetic susceptibility formula, then it is given as M vector upon H vector. So this is the formula of magnetic susceptibility, and if you substitute the value of H vector in this equation, so let us consider this is equation 4, and substitute the value of H vector in equation 4. So what you get, M vector upon minus M vector, so which is equal to minus 1. So magnetic susceptibility which is equal to minus 1, it indicate in a superconducting state, or when a superconducting material is placed in magnetic field and cool below its critical temperature, it behave as a diamagnetic material. And it will show the phenomena that is diamagnetism. Again, if you consider the relative permeability, one more important term, that is relative permeability. Its formula is mu r, which is equal to relative permeability 1 plus psi m. So this magnetic susceptibility denoted by symbol psi m. So relative permeability, which is mu r, which is equal to 1 plus psi m, and we know that the value of psi m is minus 1, so 1 plus minus 1 it becomes 0. And these two equations, that is the equation of magnetic susceptibility and relative permeability, indicate that the superconducting material it is act as a perfectly diamagnetic material when the critical temperature below its critical temperature, when a temperature it is critical temperature it is greater than the normal temperature, when it is placed in magnetic field, so it will expel out this magnetic field and behave as a diamagnetic material, and it will shows diamagnetism. So this is all about the Mesner effect. In next lecture we will discuss the next important point of this chapter. Thank you.